Welcome back. We're going to try a little new piece of technology today that'll allow us to actually write some stuff that is pretty hard to put into PowerPoint. So we're going to start on section 10.4. And 10.4 deals with convergence tests using comparison. Now, there are two types of comparison tests. So in this video, we're just going to talk about the first one, and then we'll make a second video for the second one. The first type is what's called a direct comparison. Its advantage is that it makes sense. It's very intuitive. The disadvantage is that sometimes getting the inequalities to work out can be a little bit tricky. So here's the basic gist of it. Suppose we have A sub n less than or equal to B sub n less than or equal to C sub n, and all of these are greater than or equal to 0. So this is a test that only works when you have positive terms, and we'll have to deal with the issue with negative terms later on. So we have 3 sequences in a row where this inequality holds for all n, and we want to talk about the associated series and what can we say about them. Well, first of all, if the sum of the A sub n's is infinity, in other words, it diverges, well then obviously the bigger ones, when you sum them, are going to also diverge. Okay, so that's a fairly straightforward one, and it makes sense. If we have something smaller that goes off to infinity, then obviously the bigger one has to do the same. Similarly, if the largest one converges, so it approaches some number L, then obviously the smaller ones will also converge. Okay, so intuitively this makes sense. We're dealing with almost positive things, so if it diverges, it has to go off to infinity. So if the smallest one goes off to infinity, well, then the bigger ones have to do the same. If the largest one doesn't go to infinity, it converges to a number, then the smaller ones would also have to stop and not go up to infinity also. So it's a very intuitive technique. The problem with it is sometimes we have to pick what our sequence we're comparing with is. So usually we're interested in this middle one. And then we have to say, okay, well, if we think it converges, we have to pick some C sub n's to prove it. If we think it diverges, then we have to pick a smaller one that diverges. So let's do this with an example here. Let's say we want to look at, does the sum n equals 1 to infinity, 1 over n squared plus 5 converge? Now again, our tests that we have thus far, we of course have our geometric series, we have our nth term test which can show divergence, and we have our integral test. I want to sort of stay away from them, although this one I guess you could do by integral test as well. But I want to think, well, gee, what series do I know that converges or diverges? I suspect it does because we know that the sum n equals 1 to infinity of just 1 over n squared converges. And that was from last section. In the integral test, we showed that a p-series, which the second one is, if the p is bigger than 1, so p is 2 in this case, then it converges. We also know, move my paper here a little bit, that 1 over n squared plus 5 is always going to be less than 1 over n squared. Okay, so we have the case, so if we take our c sub n to be our 1 over n squared, and our b sub n back here to be 1 over n squared plus 5, we can then use this second line of the theorem. So we can say that this original series here does indeed converge. Okay, so when we're doing a problem, we would say, and the way we would answer this is we would say this sum converges by direct comparison to the sum of 1 over n squared. Okay, so that's the way we're going to format our answers. Looks like, sorry about that, it went out of focus there for a little bit. Still working on that particular. Let me see if I can fix that in my settings so it doesn't go out of focus like that again. Turn off the autofocus and we'll stay there. Okay, so now it shouldn't, yeah, okay, now I'll mess up. Okay, let's do another one. Let's take the sum n equals, let's see here. One to infinity of 1 over square root of, let's say, n minus 0.5. I had to make it 0.5 so that we don't get a negative inside of our square root. Well, again, I look at the thing I want. Gee, if I got rid of that 0.05, I want to compare to the sum n equals 1 to infinity of 1 over root n. And we know that one diverges. Again, it's a p-series with p equal to 1/2. So we suspect it diverges, and in this case we can prove it because one over root n minus 0.5 is always going to be greater than let me see here, 1 over root n. Okay. Why is that the case? Well, if I grow a denominator, if I make the denominator bigger, it makes the whole fraction smaller. If I make the denominator smaller, it makes the whole fraction bigger. Okay. And so in this case, we will be taking this one to be our a sub n. And we can conclude that our original diverges by comparison to is. So direct comparison is nice because it really does make sense. The only problem you run into with direct comparison is that sometimes getting these inequalities to go in the right direction is going to be a problem. For instance, if this minus here had been a plus instead, my inequality would have gone the wrong way. So if we go back to where we started, we have to start with them in this order. And again, this middle one's the one we generally want to be looking at. So finding the a sub n and the c sub n can be tricky. So you first have to have an intuition of whether it converges or diverges. If you suspect it diverges, then you're looking for something smaller that diverges. If you suspect it converges, you're looking for something larger that we know converges. And when it works really fast and it's very easy. The problem is these inequalities going in the wrong direction sometimes can give you fits. For that, we'll do the second comparison test in this section, which is limit comparison. And that will avoid that issue. It has a couple things of its own, but it does avoid this whole issue of getting these inequalities right. So we'll stop this one here, and then our next video will be on that limit comparison test.